All right, here we are again talking about limits with definition, formal definition this time of a limit. And from chapter 1.2, we're a little bit more into it now, so we are going to look at this a little bit more closely with a formal definition. Formal definition says let f be a function. Okay, so defined on an open interval containing c, and let L be a real number. So we have the limit as x goes to some c value. If you need to review the previous video, you can. Of f of x will give us some L. Okay? Which means that for each epsilon, this is E's epsilon, that's greater than 0, there exists a delta, right, that's greater than 0, such that if that difference of c, right, from x to c, is greater than 0 but less than some delta, then that will produce the function, a number within the function range that will tell us within that epsilon. All right, so what does that mean graphically? So let's look at it graphically really quick. We can see that here we have our c value. Here's our function. Okay, it's just cruising along doing stuff. And before, we wanted to talk about getting arbitrarily close on either side. Well, now we're defining a little bit more. What does it mean to be arbitrarily close? If there's a c value and we can find some very, very small number on either side of c, some delta, that if we plug in that number into our function, we can find that number and it will produce a y value that will be a little bit either above that L, right, which is the epsilon change, or it'll be below that L value. And we want to see if we can figure out what's the range of those numbers that we can do. All right, so that's basically what we're doing. Don't get too wrapped up in the delta and the epsilon, other than they're just, like if this was a 3, then I would go to 4 and 2. Numbers on either side that would produce some y value, and we could plug that in and find out what those numbers are getting really close to. Okay, so that's really what we're looking at. Let's look at an example. All right, so this first example is where we're given finding a delta for a given epsilon. So we're given a limit. Here's the limit as x goes to 3 of 2x minus 5 equals 1. It says, all right, find delta. Find a number such that when we take the absolute value of this, that it will be within 0.01 of our L value. So the y's can only increase from L plus 0.01 and down 0.01. Whenever the delta, or this value of x minus 3, is either greater than 0 or less than the delta. So we need to find that delta. What is that x value that gets us within the range of 0.01 of that y value? So remember, from the definition that c is 3, so because it's x minus 3, we start by simplifying given this information, and we get 2x minus 5 is equal to 1. We basically take this function, we set it equal to what they gave us as the y value, or this L value. The function, so this is the y or that L value, right? Okay, so we're on track. We keep going. And we see that we can subtract 1 from both sides. And we get 2x minus 5 minus 1. We subtracted the 1 from both sides. We get it to 0. But we don't really want 0, right? We want it to be where it's 0.01. That was the given in the problem. Find that L, or find that epsilon that's either 0.01 greater than the L, or 1, right? Where is it 0.01 greater than 1 and 0.01 less than 1? That was the given L that we had. And what we do is now we can simplify. We can go to the next step and we simplify. So negative 5 minus 1 is negative 6. So we have the absolute value of 2x minus 6. When is that? For what x values is that number less than 0.01? We can factor out a 2, right? So we get 2x minus 3. So all the algebra right now is working out nicely. We can put that 2 on the outside. That doesn't hurt the absolute value bars because we're not subtracting anything out. We're simply dividing something out. We would end up with 2 times x minus 3 is less than. When is that less than the 0.01? We end up dividing by 2, and we find that the absolute value of x minus 3 is less than 0.005. So, hey, we have concluded that those values are going to be less than 0.005. If we put 0.005 in as a value, we will get as our delta. Then, if we use delta values of 0.005 within 3, so 3 was the x, we want to find out what 0.005 of 3, 0.005 less of 3. Those numbers, if they go up, they will produce y values, right? Y values within, or epsilon values within 0.01 of 1. Okay? So we can conclude that, to go back to our original picture here, those delta values were 0.005. So remember, we had 3 here. So we had 3. We put 3 and we put 0.005 here and less 0.005. Those numbers will go up and they will create epsilon values of 1, 0.001. That will help us find here. So we had a 0.01 and a minus 0.01 to get an L value of 1. All right? Have a great day. Talk to you later.